Hello, my dear students. Welcome to one more lecture on econometrics. In this lecture, I'll give you an introduction about a concept called multicollinearity in econometrics. Okay. So when we discuss about the assumptions of econometrics, the last assumption that we have discussed is the multicollinearity. That means the regression model assume that there is no multicollinearity in our regression model, or there is no multicollinearity. Okay, so actually what this multicollinearity is? This multicollinearity concept is one of the oldest concept in econometrics, and it is the most misused both in econometrics text as well as in empirical literature. Okay, and the concept multicollinearity was first introduced by, or this concept was due to Ragnar-Frisch. Okay, so he introduced this concept called multicollinearity in econometrics. So this is not a concept, basically it is a problem in regression model. Okay, so this is basically a problems when you will have, or when you have a multiple regression models. Okay, when you have a simple regression model in which one dependent variable and one independent variable, we should not expect this kind of a multicollinearity issue. Okay, so the multicollinearity issue is basically the existence of perfect or exact linear relationship between two explanatory variable or more than two explanatory variable in a multiple regression model. Okay, so when we say this definition, you have to understand that the existence of perfect. What is meant by perfect? That we will see later. Okay, what's perfect and what is mean by linear? Exact, it should be exact linear. Okay, so what assumption is there should not be perfect linear relationship between two or more explanatory variable in our regression model. Okay, so multicollinearity is not about the dependent variable. The issue of this multicollinearity is not about the error term, it's about independent variables. Okay, not about a single independent variable, but if you have more than one independent variable in your regression model, then only you need to worry about this multicollinearity issue. Okay, yes. But why this problem is very important? Why this multicollinearity? Why we are learning this multicollinearity? It is because of the assumption of CLRM. Okay, but the CLRM, that means classical linear regression model, is assuming that there should not be multicollinearity. Okay, yes. So we will see whether in real economic problem or real analysis we will whether we will encounter this issue of this multicollinearity. Okay, that we will see later. And if you look some books, in some book they have written collinearity, and some book they have written multicollinearity. Okay, and in some they have written the serial correlation, something like that. Sorry, yeah. So this collinearity and multicollinearity both are same, even though there are some differences. Okay, so collinearity is mainly used to denote the exact or perfect linear correlation between two independent variables. Okay, whereas multicollinearity, as the term says, multi, that means it's here about the correlations between more than two independent variables. Okay, but in some book they have used this term interchangeably. Okay, so collinearity and multicollinearity both are intended to give the same idea, that is the relationship between what relation? Exact, linear, perfect. Okay, relationship between two or more independent variable in a multiple regression model. Okay, then why this multicollinearity is matter, or why this classical linear regression model is assuming that there should not be a multicollinearity? Let me give you two examples. Okay, so if you look at the first equations, it is agriculture yield is a function of fertilizer and pesticides. Fertilizer and pesticides. Agriculture is a function of pesticides and fertilizer. What does it mean? If you increase the use of the fertilizer and pesticides, or if you adopt this, if you use this fertilizer and pesticides in a area in an agricultural field, agriculture yield may increase. Okay, yes, but you think about a situation that a farmer, he is applied both fertilizer and pesticides into a field, and after the harvesting time, or after harvesting, when he checked the agriculture yield, the quantity of the agriculture yield, he realized that the agriculture quantity has the yield has drastically increased. Okay, but he could not tell you whether I have got this whether this agriculture yield or this increase in the agriculture yield is due to the adoption of, or is due to the application of this pesticides or fertilizer. Okay, we cannot say because we have used both. Okay, yes. Similarly, when you come to the consumption equation, okay, so in a consumption function, we know that consumption is positively related to income and wealth. Okay, and suppose a person's income has increased. A person's income has increased. It is usually we can hypothesize that when a person's income increase means what? His wealth also increase. Okay, or if a person wealth increase, what does it mean? His income is also increasing. Okay, so this wealth and income both are highly related variable. Okay, and if you look at one person's consumption, it has drastically increased, but we cannot say whether this increases in consumption is due to the increases in income or increases in the wealth. Okay, so this kind of a problem will encounter in regression when we use two independent variables that are highly correlated with each other. Okay, and now when I say about the collinearity or multicollinearity, there are two different types of collinearity. Okay, first one is perfect collinearity and second one is imperfect collinearity. Okay, so what is the assumption or what is the idea? There should not be perfect correlations. Okay, we can have some relationship, but the relationship should not be perfect. Okay, then what is perfect and what is imperfect? You look at this equation. Y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus u. Okay, it means that y, a variable, depends on x1, x2 and x3. Okay, and we have an hypothetical example of all these three variable, independent variable, x1, x2, x3. Okay, you look at this x2, what you can see or what you can understand from this variable. If you look at this x2, this variable is exactly is 5 into x1. Okay, 10 into 5, 50. 15 into 5, 75. 18 into 5, 90. 24 into 5, 120. 30 into 5, 150. So x2 is exactly equal to 5 into x1. What does it mean? The changes in x2 is exactly the ratio changes. Okay, that means x1 and x2 both are increasing at a constant ratio of change. Okay, so if you divide x1 with x2, you will get a value 5. Okay, yes, you will get the uniform value if you divide 50 plus divide by 10, 5, 75 divided by 5, 15, 5. Okay, so it x2 is basically x1 into 5. Okay, so both are moving in the same direction and it is linear. That means both are increasing the constant ratio of changes. So if you find out the correlation between these x1 and x2, you will get 1. Okay, yes. Now if you find out the correlation between these x3 and x2, or x3 and x1, okay, this is the x1, this is your x2. What is the correlation between these two? Is it linear? No, we cannot say it's linear, because when x1 increases, x3 is also increasing, but not with a constant ratio of changes. Okay, and when you calculate this correlation between x1 and x3, we are getting 0.99. Okay, it's not is equal to 1 but less than 1. This is what we call imperfect collinearity. Perfect collinearity means the correlation value is either -1 or +1. Okay, and if uh, imperfect collinearity means what? Less than this -1 and +1. Okay, yes. Now we have an equation, or we have a multivariable equation, or we have an equation with two independent variables. Okay, yi is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus u. Okay, here what you have to check, here look at this beta 1, beta 2 and beta 0. We have three coefficients. We have three variables y, x1, x2, one dependent and two independent, and we are having two slope parameters and one intercept parameters. Okay, so how we can estimate this value of beta cap 1 and beta cap 2? Okay, for that there is an equation. What is that equation? It is sigma small y x1 into sigma x2 square minus sigma y into x2 into sigma x1 x2. Okay, divided by sigma x1 square into sigma x2 square minus sigma x1 into x2 square. Okay, so this is the Euler's equation for calculating beta 1 for a 3 variable model. Clear? Yes. And now all these y, x, all these are deviation. Okay, it's not actual y but y minus y bar. Okay, then how you can find out beta 2, beta cap 2? Say whenever you have given x1 you put x2. Okay, wherever you have put x2 you put x1 there. That's in numerator. Okay, denominator it would be the same. So this is the denominator for the first equation and this is the denominator for the second equation. Both will be the same. The denominator will be the same, only the numerator will change. Okay, so look at this here x1, x2, here x1 square, x2 square, here y into x2, here y into x1, x1 into x2, here x1 into x2. It won't change. Okay, then how we can find out the beta cap 0? It is y bar minus beta cap 1 into x bar 1 minus beta cap 2 into x bar 2. Okay, then we have to understand that if the multicollinearity is perfect, or if the correlation is perfect between this x1 and x2, then the problem is these things sigma x1 square into sigma x2 square minus sigma x1 into x2 whole square, this will always equal to 0. Okay, the denominator will always is equal to 0, and that's why in the case of perfect multicollinearity, x1 will be an exact function of x2, and due to this fact, okay, the denominator will be always is equal to 0, and a numerator with any numerical value divided with 0 will be indeterminate. Okay, we cannot find out the value of this beta cap 1 and beta cap 2 because this beta cap 1, beta cap 2 are perfectly correlated. Okay, so what is the problem with the multicollinearity? If the multicollinearity is perfect, then we cannot estimate the parameters of beta cap 1, beta cap 2 and beta cap 0 because in both slope coefficient the denominator will be always equal to 0 and any value divided by with 0 will be invalid, or we will not get any value for this expression. Okay, so that's the problem with Euler's estimation when you have perfect multicollinearity. Is it okay? Yes. Now, what will be the problem with Euler's when we have imperfect multicollinearity? Okay, for that we have to check the variance. Okay, so in the case of the imperfect multicollinearity, we are able to derive the value of beta cap 1, beta cap 2 and beta cap 0. No problem there. We will get the values. Okay, but the problem is with the variance. So what will happen to variance? Okay, as the correlation between x1 and x2 increases, the variances of beta 1 increases rapidly in a nonlinear fashion. As a result, the confidence intervals will be wider, and because of this thing we mistakenly conclude that the true beta 2 is indifferent from 0. What does it mean? Okay, it means that when the correlation between two variable x1 and x2 is increasing, okay, then the variances of this beta 1 and beta 2 will also increase. Okay, so what's the problem with if the variance increases? The confidence interval in the hypothesis testing is constructed on the basis of variance. Okay, so if variance is high, the confidence interval will be very wide. Okay, if the confidence interval is very high, we may accept or reject a true or false null hypothesis. Okay, that means we may commit the mistakes in the hypothesis testing. Okay, so that's the problem with imperfect collinearity. Okay, so here you look at the variance of beta 1. So in a multiple regression, if you have three variables, okay, then variance of beta 1 is the slope, will be this small sigma square, that means standard error, divided by sigma x1 square into 1 minus correlation between 1 to square. Okay, or it is small sigma square divided by sigma xi square into various inflation factor VIF. Okay, so what is the value of this VIF? How we can find out the VIF? VIF is nothing but 1 divided by 1 minus R12 square. That means correlation between 1 to square. Okay, so a variance of beta cap 2, how we can find out? The same. Okay, a small sigma square divided by sigma x2 square. Okay, here we have used x1, but here we are using x2 into 1 minus R12 square. That means small sigma square divided by sigma x2 square into VIF. Okay, yes. So if we find out this VIF and the value of the small sigma square and sigma x1 and x2 square, we can find out the variance of beta cap 1 and the variance of beta cap 2. Okay, and if you put a root symbol for both this equation, it will be standard error. Don't forget that. Okay, so now what we have discussed so far. First thing, what is multicollinearity? Okay, in regression, why we are assuming multicollinearity? Then what is the collinearity and multicollinearity? What is the perfect and imperfect collinearity? What is the problem with multicollinearity in the OLS? Okay, two problem. If the correlation is perfect between two explanatory variable, then we are not in a position to find out the value for beta cap 1 and beta cap 2. That means slope coefficient will be indeterminate. Okay, and if the values of this, if the correlation between two values are imperfect or less than 1, okay, then we will be able to derive the value for these coefficients, but their variance will be very high, and due to this high variance, the confidence interval will be very wide. Due to this fact, we may accept false null hypothesis, or hypothesis testing based on this variance may go wrong. Okay, yes. Now let us check how we can what's the problem with this, what is correlation, what is multicollinearity, and what is the problem with this multicollinearity. That we will see in a by taking a real example. We are going to see what is multicollinearity and how this is affecting. Okay, yes. So look at here, I'm not going to do this, okay, but I'll show you the file which I have already done. Okay, so here what I'm going to do is, I have two variables here, three variables, y1, x1, x2. Okay, so this is the same thing I have given to you. This thing x1, x2, x3. I am adding a y variable here, and this y values are 12, 18, something like that. Okay, so this is my data. Okay, yes, yes. Okay, now what I'm going to find out, I'm going to find out beta cap 0, beta cap 1 and beta cap 2, two slope coefficient and one intercept coefficient. Okay, so for that what I have to do, I want to find out small y. Small y is nothing but actual y minus y bar. Okay, so it is 12 minus 26.8. okay, it is minus 14.8. you do it for all, you will get the values. Okay, then you find out x1, x2. Okay, then find out y into x1, y into x2. Okay, then x1 into x2, x1 square, x2 square. Okay, yes. Now what happened, you look at this value, this is correlation is perfect. How you can understand that? If you find out the correlation between this comma this, you will get 1. Okay. Yes. So because of these things, what is the problem with Euler's if the correlation is perfect? I'll show you. Okay, so look at this is the equation for the numerator. What I am going to do is I am going to multiply G7, that means 382.4 into 6080 minus 1912 into 1216. I will get the numerator. Then what is denominator? Okay, it is x1 into x2 minus 6080 minus then 12016 square. Look at this denominator here, numerator also 0. Okay, so look at this, denominator is 0. In this problem numerator is also 0. Okay, so it is not guaranteed that always the numerator is 0. Okay, numerator can become 0 and non-zero, no problem, but denominator will be always is equal to 0. Look at the second equation, beta cap 2. It is same thing. Okay, 1912 into 243.2 minus 382.4 into 243.2, 12016. Okay, we are getting 0, and denominator I know what I told you that it is same for both equation. Okay, so if it is beta 1 this denominator is 0, then this also will 0. Okay, then if you divide 0 with 0, it is indeterminate. It is indeterminate. So is it fine? We cannot find out the correlation, or we cannot find out the beta cap 1 or we cannot find out the values of these Euler's estimators. Okay, so that is the first question. Okay, so since this cannot be calculated and beta 0 will also 0. Okay, so that's also we cannot calculate. Now we are coming to the second issues. What is that? Here if you look at this correlation between this x1 comma x3, it is not perfect but it's imperfect, less than perfect, 0.99582. okay, so what's the issue here? Here the issue is we can find out the same, we can go through the same procedure, and when you find out this beta 1 numerator, we are getting a value, and when we find out the denominator, we are getting some values. Okay, and finally beta 1 is 1.80, beta 2 is minus 0.4, and beta 3 is minus 3.64. okay, yes. So for the first model, for the first data, since this x1 and x2 are perfectly correlated, we are not in a position to find out the coefficient. But in second equation, there is no problem, we can find out the value for this coefficient. Okay, so after getting this equation, what you can do, you can find out the y cap. Y cap is nothing but 1.809 plus 0. Yeah, it is not that, no. Yeah, anyway, don't P18. Yeah, it is. Yeah, actually, so this is Okay, so this is beta 2, this is beta 3, and this is beta 1. Okay, so if you find out this y cap, we are getting the values, and if you find out the y cap, then we can find out u cap, because u cap is y minus y cap. You just click here, you can see that it is y minus 12 minus 12.05. We are getting around minus 0.05. Okay, then you can find out u cap square. Okay, and if you add this u cap square, we are getting, this is what we called RSS. Okay, now if you come here, yeah, it is called standard error. It is called standard error. Okay, small sigma. I have told you that how we can find out this small sigma. Okay, yes, so I'm not going to discuss it. Then after this, what we can do, this is what we called H23 minus 2, standard error of the regression models. Okay, so it is RSS is equal to 41.41 divided by 2. That means n minus how many parameters we have, how many things we have to do. We have to find out two values, or we are having two independent variables, so it is 2. Okay, so it is x square. Then if you find out the square root of these things, we will get this value, small sigma. Okay, so small sigma is 4.55, but small sigma square is equal to 20.70. Okay, then you know that what is x1 square, it is 243 x1 square. Then what is correlation between these two values, it is 0.995. What is r square, it is 0.995 into 0.995, it is 0.991. Okay, then denominator is equal to 1.99. Okay, that is mean by denominator is what, sigma xi square divided by 1 minus r square, sigma xi square into 1 minus r square. Okay, so what is variance of beta 1? It is sigma small x square divided by n into, so look at this equation, this is the equation. Okay, so we are going to find out this one. Okay, so what we are going to do, it is small sigma square. Okay, this is sigma x1 square, this is 1 minus into 1 minus r2 r12 square. Okay, so that's we are going to find out here. So this is sigma xi square into r square into 1 minus r square, sigma xi square into 1 minus r square. Okay, then this is, sorry, and this is what, variance of first, that means sigma small sigma square divided by 1.99, it is around 10.35. Okay, then if you find out the square root of this thing, we are getting this 3.218. Okay, so this is for, I think, first equation. Is it for first or second equation? No, for second equation. In first equation we cannot find out anything. Okay, in second equation this is the for the first variable, and this is for the second variables. Okay, so in second variable also this value will not change, and this is changing this. Yeah, okay, so this will be, I think, okay, so this is for the first variable, I think. This is for the first variable, and this is for the second variable. No. Okay, so since all these coefficients are 0, we cannot find out the r square. Okay, so this is basically sigma xi square 240 and j 243. Okay, actually this is not this, actually this is this value, not that one. 242 point, yeah, both are same. Okay, and here what we are going to do, we are taking x3 square, not x2 square, but x3 square, and here is also r square is equal to 0.995. Everything is fine, but the denominator is different. Okay, what is that? Yes, sigma x I square into 1 minus r square. It is around 53.246. Okay, then you can find out the variance. It is nothing but small sigma square divided by sigma xi square into 1 minus r square. Okay, it is variance, and this is the root of the variance. Okay, yes. So what we have done so far, we have find out these things. Okay, then what is this VIF? It is 1 minus, or 1 divided by 1 minus R1 2 square. Okay, look at how we can find out these things. Okay, so look at these things. Yes, 1 divided by 1 minus 0.991 is around 121. Okay, and what is this? No, it is not needed. Okay, yes, it is sigma, small sigma square divided by sigma xi square. Yeah, it is variance. Small sigma square divided by sigma xi square. Okay, yeah, these things. Okay, then that is these things. Yeah, if you multiply this thing with this, okay, so this thing is the same. You can find out these things using this method also. Okay, so you can find out the this thing using this thing and this thing. That means you can find out the variance of beta 1 and beta 2 using small sigma square divided by sigma x1 square into 1 minus r12 square, or small sigma square divided by sigma x1 square into VIF. Here VIF is around 121.66. Okay, yes. Now I'll show you what will happen if the correlation between two variables is increasing. Okay, so look at these things. This is 0 point, this is 0, that means correlation is equal to 0. Here assume that our VIF is equal to 1, and this is our variance of first. Okay, and this is our second variance. Okay, yes, you look at the variance when the correlation is becoming stronger and stronger. What is happening our variance? Okay, look at this variance is around 0.85. now the correlation is equal to 0. That means if the correlation between two experimental variable is very low, then the VIF will be very low, then the variance will be very low. Now you look at the correlation has increased to 0.1. what happened? VIF is increased, variance is also increased. Okay, this also increased. For both variants are increasing. Okay, and look at these values. When 0.85, VIF is 3.6, and it has become 0.3. Okay, 0.01. Now if you see, when the correlation is the 0.99, VIF is increasing. Okay, then variance has become 4.27, and this is 0.16. when the correlation is equal to 1, you are not in a position to generate VIF or variance of 1 or variance of 2. Okay, yes. So VIF, when you can find, when the two independent variables are perfectly related, then you will have this situation. You cannot find out the coefficient as well as you cannot find out the variances. Okay, and the second case, when the variance are not perfect, so when the correlation is not perfect but imperfect or less than 1, even though you can find out the coefficients, but when your variance will become higher and higher. Look at this. Okay, if the correlation is 0.99, the variance is around 4.28 and this is 0.16. Okay, so this variance will increase. Okay, so this is the problem with correlation, and there is a one more term called tolerance ratio, TOL. Okay, so this TOL is the just opposite of this VIF. Okay, it is nothing but 1 divided by VIF. 1 divided by VIF. Okay, so that is the problem with multicollinearity. When multicollinearity is perfect, there's a problem. What is that? We cannot estimate. When the correlation is imperfect, we can estimate, but there's a problem. What's the problem? The variance will become high. We cannot do a hypothesis testing with this high variance. If we do such hypothesis, then it may go wrong. Okay, so that's the problem with the correlation or this multicollinearity. Okay, so let me list out the problem with this multicollinearity or consequence of multicollinearity. Okay, so the first consequence is, as I discussed, okay, the Euler's method cannot produce parameter estimates. We cannot produce any parameter if the multicollinearity is perfect. Okay, the second one, if the multicollinearity is imperfect, okay, then the regression coefficients, although determinate, possess large standard error. Okay, which means that coefficient cannot be estimated with the greatest accuracy or precision. Even though we can estimate the equation, but we cannot expect accuracy or reliability or precision. Okay, so even though the third problem is, even though the Euler's remain blue, Euler's will be best linear and unbiased because the linearity or unbiasedness properties are not associated with this problem. Okay, so in the presence of this multicollinearity, the Euler's will become best linear and unbiased, but large covariance and variance make precise estimation difficult. Okay, so there is no problem with estimation. The problem is with the hypothesis testing. Okay, and the second problem with this hypothesis testing is that confidence interval will be much wider, leading to the acceptance of a null hypothesis that is false. Okay, yes, and and because of these things, because of the large variance and covariance, P ratio tend to be insignificant. Okay, and R square will be very high in spite of the insignificant determinants of variables. Okay, so even though the values are insignificant, it shows the highest R square. Okay, so due to this fact that you may accept that, or you may agree that the changes in the dependent variable are much explained by the independent variables. And the last consequence is OLS estimators and their standard errors are much sensitive to small change in data. So in the presence of correlation, okay, if you change the sample, if you add one more observation or if you delete one observations, okay, it will have high impact on standard error and Euler's estimator. That means Euler's estimators and standard error will change the sign and as well as will change the values drastically when you make a small changes in the data. Okay, so that's the consequences with this multicollinearity. Okay, so that's all about today's sessions, and tomorrow the next video I will come up with an example, real examples, and how we can check multicollinearity in a real time examples. Okay, so thank you.